Okay. Good morning, people. I've
Good
started
morning, sir.
recording.
Good morning, sir.
Yeah, good
Good
morning.
morning, sir.
Time. Good morning, everyone. I have started tracking your attendance as well. You don't have to write down your attendance from today onwards. I've attached a special software that will track your, just like I put the detailed attendance report yesterday. Today onwards, I'll have a detailed attendance report as to who is joining and who is leaving in between. What is the total percentage of a student having joined a particular lecture session as such. So you don't have to write down your names in the chat box anymore. I have an extension attachment now to this whole issue as such. Now, before we go ahead, I want somebody to just give us a brief idea of what we had done yesterday quickly, so that it will be a revision for all. And it's not necessary that only one person has to speak, others can also join in. दिव्या नलावडे मी म्हटलं नका लिहू आता, काही गरज नाही, लिहिलंय तर काही हरकत नाही, पण लिहायची गरज नाहीये. इंग्लिश कळत नाहीये का आपल्याला? Yeah, somebody or a group of people will please let me know what we did yesterday. What was the idea of what we were doing yesterday? Yes, please. Yes, somebody was saying something.
Mixing ratio, relative humidity,
Mixing ratio, relative humidity, and what?
absolute humidity,
Absolute humidity and vapor pressure. What are all these? What are all these? Methods of, समोर slide वर दिसतंय ना रे. Methods of expressing water vapor content in the air. Okay, these include absolute humidity, mixing ratio, vapor pressure, relative humidity, and we have to take up dew point. Yes, till yesterday I think we reached till relative humidity, right?
Yes, sir.
yes, sir.
Okay, so let us move ahead from that point. I'll just take a revision of it. Okay, water vapor is one of the most variable constituents of the atmosphere. You'll see from as little as 0.1%, it can go up to literally 4%. Of course, by volume. Huh? Uh, to measure or to express water vapor content, what we do is we use various terms such as absolute humidity, mixing ratio, vapor pressure, relative humidity, and dew point. Okay, of these, absolute humidity and mixing ratio are similar, and as both of them are expressed as the quantity of water vapor contained in a specific amount of air, but there is a difference between them. The first one, absolute humidity, is considers the mass of the water vapor in grams, and of course volume of the air. Yesterday we have seen that volume is related is in relation to the temperature. So if the temperature is going to change, the volume is also going to change, and as a consequence we move to what is understood as mixing ratio, which is more constant as compared to absolute humidity. Mixing ratio is the mass of water vapor in grams to the mass of dry air in kilograms as such, and that is why you'll see that mixing ratio, the value doesn't change so often. Okay, and that's why it's also called as specific humidity. Okay, and there is a difficulty as far as both of them are concerned, that you cannot determine them by direct sampling. Therefore, other methods are used to express moisture content. One of them is vapor pressure, and vapor pressure is nothing but the pressure of vapor that is there in the air. Okay, initially water is dry and then it starts getting moist when water tends to be added to it in molecules. Okay, there is a limit to which this a particular moist air is going to, or a particular set of air is going to absorb. That limit is called as saturated air. At saturated point of air, you will tend to have the maximum vapor pressure. I did not tell this yesterday. That's going to be your maximum vapor pressure at that particular temperature. But the fourth diagram now. But if the temperature of the air is going to rise, there is the potential for that particular air mass to absorb more water vapor will increase certainly. And at a new saturated airline, you will see that the air pressure or the vapor pressure will have increased by a significant say scale. Okay, that is as far as vapor pressure is concerned. The balance of evaporation and condensation is in fact called as saturation. We have done in absolute detail as to what saturation is all about and what saturation point is all about. Uh, then we move to what is called as, or say, what is called as the mixing ratio at different temperatures. We required the mixing ratio at different temperatures basically because we need to calculate what is called as relative humidity. Relative humidity is nothing but the actual amount of water vapor available at in a particular air mass in proportion to the total amount of water vapor that that particular air will hold. Now, you see these three flasks and they have a common temperature of 25 degrees centigrade. No, sorry. In the first case, you have only 5 grams of water vapor in 1 kg of air. But you'll see that at that particular temperature, 25, the potential to hold water vapor is 20 grams. Okay, the potential to hold is 20 grams, but actually available is only 5 grams. So 5 is what, 1/4 of 20 grams. So that is why 5 upon 20 is 25% humidity. Okay, when you double the number of water vapor to 10 grams, okay, at the same temperature, what happens is the relative humidity also doubles. That comes to 50 because now you have 10 grams of water vapor uh, to the capacity of 20 grams. So it's half of it now. And the third scenario wherein now it is 20 grams and the saturation or mixing ratio at 25 degrees is 20 grams as well, because the you have the same amount of water vapor as compared to the saturation mixture. You'll see that you're going to have it at 20. So 20 upon 20, you'll see is going to be 100% relative humidity. Now tell me an answer to my question as to if it now increases to 25 grams. If it increases to 25 grams, what will happen? In the same flask, if it increases to 25 grams, what will happen? 25 degrees centigrade and 25 grams of water vapor. Mixing ratio, however, is 20 grams. What will happen? कोणी सांगू शकेल? What will happen in that case? काय होईल? काहीतरी होईल ना? का काहीच होणार नाही?
रिलेटिव्ह ह्युमिडिटी वाढेल.
100% च्या वर जाऊ शकते का रिलेटिव्ह ह्युमिडिटी?
नाही सर.
म्हणजे काय होईल म्हणजे आता? रिलेटिव्ह ह्युमिडिटी 100 झाली म्हणजे अजून एक शब्द काय वापरला आपण त्याच्यासाठी?
सॅच्युरेशन पॉइंट सर हे झालं.
सॅच्युरेशन पॉइंट रीच झालेला आहे. त्याच्या पलीकडे तुमच्याकडे सॅच्युरेशन काय होतं? एक्सेस वॉटर वेपर विल और एक्सेस कंडेन्सेशन विल व्हॉट?
सर प्रेसिपिटेशन चालू आहे.
इथे म्हटलं एक्झॅक्टली प्रेसिपिटेशन सुरू होणार. ते 5 ग्रॅम्स जे आहे तुमचे तेवढं प्रेसिपिटेशन होणार, परत ते 20 ला येणार आणि परत थांबणार. ओके, पण आता मला सांगा की टेम्परेचर 25 च्या ऐवजी 30 ला गेलं. टेम्परेचर 25 च्या ऐवजी 30 ला गेलं. आता रिलेटिव्ह ह्युमिडिटी 100 राहील का या कंडिशन मध्ये? सी कंडिशन मध्ये 20 ग्रॅम्स आहे, 25 आहे, रिलेटिव्ह ह्युमिडिटी तेवढीच राहील का? 100?
Yes, sir.
How? Your temperature is higher. Sumedha, I think you were not there yesterday.
No, sir.
So you'll have to check here. Okay, you'll see yesterday we said that at 25 degrees centigrade, the mixing ratio is 20. Okay, at 30, the mixing ratio is now higher. As a consequence, what will happen? At 25 degrees, this will fall less. So this will go below 100% if the temperature is increased to 30 degrees. This temperature increases to 30, this will fall. कारण तेवढ्याच तेवढं नाहीये ना. Okay, it will be 26.5 upon 20 now. So rather 20 upon 26.5. So that will give you a percentage which is going to be less than 100. So it can still absorb more. Okay, it can still absorb more amount of grams. Okay, another 1.5 grams to reach the 100% humidity as such. Now, did we do this yesterday? I don't think so.
No, sir.
पब्लिक हे केलंय का आपण नाही केलेलं. ओके, लेट अस. हे इथपर्यंत रिव्हिजन होतं, इथपर्यंत समजलंय? हॅव यू अंडरस्टूड व्हॉट इज हॅपनिंग?
Yes, sir.
नसेल समजलं तर यू प्लीज आस्क मी. एकच जण म्हणतोय समजलं, बाकीच्यांचं काय?
हो सर समजलं.
Okay, let us move ahead. Now, let us assume that when the water vapor content in the air remains constant, a decrease in air temperature results in an increase in relative humidity. मी आता काय सांगितलं तुम्हाला हे, की इथे फक्त उलट लिहिलेलं आहे. इथे काय झालेलं आहे, मी 25चं 30 केलं होतं टेम्परेचर, बरोबर. इथे बघ हे काय म्हणताय ते आता. वेन द वॉटर वेपर कंटेंट इन द एअर रिमेन्स कॉन्स्टंट, आहे तेवढंच आहे, but there is a decrease in air temperature, it will result in the increase in relative humidity, and conversely an increase in the temperature will cause decrease in the relative humidity. शेवटची लाईन जी होती ती आपण इथे अप्लाय केली होती. Okay, an increase in the temperature will lead to a decrease in humidity. It will fall down to somewhere around 99 to 94. I am not very precise with my mathematics here. Okay, so this is what is happening. Now, in nature, there are three major ways in how air temperature will change. Okay, over a relatively short span of time. Daily changes in temperature, daylight versus night time. Diurnal change ज्याला आपण म्हणतो. Daily range temperatures are higher and evening temperatures or night temperatures are lower. So that is how temperature change in first condition will take place. Second, temperature changes as a result as air moves horizontally from one location to the other. Temperature will change if air is going to move. Okay, and then third, temperature changes caused as the air moves vertically up. So moves horizontally, that is advection, and moves vertically, that is convection as well. Okay, temperature changes caused by air movement vertically in the atmosphere as such. Okay, just to go into a bit of details of that. Okay, you'll see that as far as daytime is concerned, okay, lowest temperature is just before 6 a.m. and then it starts rising. Okay, you'll see that the highest temperature is somewhere around 4:30. Okay, which is not so the case as far as tropics is concerned, but let us assume it. Okay, because with latitude ही जी हा जो पीक आहे आणि हा जो लो आहे हा थोडा थोडा शिफ्ट होतो. Okay, as far as tropical conditions, आपण अगदी प्रिसाइसली पुणे म्हणायचं म्हटलं तर मॉर्निंग 5:30 4:05 च्या आसपास लोएस्ट टेम्परेचर आणि अराउंड 2:30 to 3 you will have the highest temperature as far as the latitude of Pune is concerned. This is how the curve goes as far as the night curve is concerned, or rather sorry, the relative humidity is concerned. Okay, because the temperature is lowest, okay, you'll have to read it like this. Okay, because the temperature is lowest, relative humidity is highest. Okay, पाऊस पडण्याची शक्यता ही ह्या वेळेस जास्त आहे. Okay, and highest temperature will have the lowest humidity. Okay, then now let us understand this once again. Okay, what is happening there? They have changed the temperatures. You'll see that here the temperature, first case the temperature was 20 degrees. Okay, then it is 10 degrees and then it is 0 degrees. So they have changed this as such. Okay, now let us see what is the mixing ratio. 10 20 10 0 20 10 0 put together 20 20 10 7 0 3.5. लक्षात ठेवलं? लक्षात ठेवा 14 7 3.5. ओके, किती होतं? 20 30
14.
14. Then
7 and 0.5. 7 and
7
3.
and 3.5. See, 3.5 is half of 7, 7 is half of 14. असं सुद्धा आपण लक्षात ठेवू शकतो हे. But of course, that is the mixing ratio for these individual temperatures. Now, you have 1 kg of air everywhere. Okay, याच्यामध्ये you have 7 grams of water vapor. 7 grams of water vapor. याची कॅपॅसिटी किती आहे? 14 ची आहे किती? 7. So relative humidity is 50. येतंय लक्षात?
Yes,
हो
sir.
सर.
Yes. Now, the second case is the temperature has fallen down to 10, but the amount of water vapor is the same. Mixing ratio is same. The amount of this is same. So the mixing ratio is 7. The amount of water vapor available is 7. Both of them are equal. So the relative humidity is going to be 100%. येते लक्षात? Okay. And in this case, they have changed the amount of water vapor is 3.5 grams, but the mixing ratio is also 3.5. Okay. So at 0 degrees, okay, with 3.5 grams as mixing ratio and the amount available being 3.5, it will be 100, the relative humidity will be 100% once again. Okay. So this is, okay, and the reverse will be true. Okay. When the temperature will increase, of course, the mixing ratio value will increase. So it can accommodate more and more water vapor as well. Okay. A few facts. The dew point temperature, or simply dew point, is the temperature to which air needs to be cooled to reach saturation. What is saturation? Saturation is also 100% relative humidity. Okay, you'll see these ice cubes here, and you'll see this, the outer side of this glass has condensation because it has crossed saturation level as such. In nature, cooling below dew point causes water vapor to condense. Okay, and this condensation will be in the form of dew, it will be in the form of fog, or it will be in the form of clouds. Dew and fog are near the surface, clouds are up in the sky. The term dew point stems from the fact that during night-time hours, objects near the ground often cool below the dew point temperature and become coated with dew. Unlikely relative humidity, which is measured of how near the air is being saturated, dew point temperature is a measure of actual moisture content of the air parcel. Okay. Actual water vapor content of the air remains unchanged. The mixing ratio remains unchanged. But remember, this unchanged is with regards the temperature, degrees Celsius. What is the degrees Celsius? X degrees centigrade as such. Okay, if the temperature changes, of course, the mixing ratio will change. Okay, कुठं बघितलं आपण हे? This is the mixing ratio. It is changing as the temperature is changing as well. आलं लक्षात? Now, I don't know how many of you all have heard of humidifiers and dehumidifiers. आजकाल आता ही इलेक्ट्रॉनिक उपकरणे आपल्याकडे पण मिळायला लागलेली आहेत. Okay? In summer, stores sell dehumidifiers. As winter rolls, they start selling humidifiers. Okay, this is nothing but a specific form of air conditioner, humidifier and dehumidifier as such. Okay, I'll not go into the details of this. We'll move ahead. Okay, there are spatio-temporal variations in the rate and the amount of evaporation due to various factors. Okay, what are the factors which affect evaporation? Vapor pressure on the surface, vapor pressure of the air, wind velocity, and salinity of the water bodies as such. Obviously, you'll see that if the vapor in the air is going to be less, okay, the drying is going to be faster. If the vapor is going to be more, the drying is going to be slower as such. And you'll see that it is always drying is a function of vapor pressure of water surface, vapor pressure of air. Okay, so if you have water and this is water, this is air. Okay, the steeper the gradient between them, the faster will be the exchange. Now, if you have to look at the latitudinal variation of precipitation and evaporation as such, this is the equator, these are the doldrums. Okay, you'll see that this is the evaporation curve. Okay, this is the evaporation curve, and the dotted line is the evaporation curve, and the continuous line is the precipitation curve. Okay, so you have a huge amount of surplus precipitation, and that's why you have more rainfall along 0 degrees. But this part to this part here, and this part to this part here, the evaporation is more. You can see here. And once again, when you cross 40 degrees, 45 degrees, you'll see that the precipitation tends to be higher as compared to this. And interestingly, you'll see that precipitation in the southern hemisphere is more as compared to the precipitation in the northern hemisphere. These are a few things that we have to keep in mind about evaporation. Okay. The rates of evaporation at times are affected by ocean currents. Before that, wind velocity. Okay, you'll see that it will affect the amount of evaporation that takes place. Okay, why does it happen so? Okay, you'll see that let us say this is the surface and this is the temperature of a particular area, say x degrees centigrade. Now, this temperature is of the air around also. Let us assume it in that particular way. Now, if this is stable, okay, no changes will take place. As a consequence, evaporation will not take place. But you have some wind blowing, okay, and you're going to have new particles of air of a different temperature coming up. Obviously, this will change the rate of evaporation. Okay, so is the case as far as salinity of water body is concerned. Okay, higher salinity will lead to evaporation, lower salinity will lead to lesser evaporation, and so on and so forth. Okay, so vapor pressure of water surface, vapor pressure of air surface, wind velocity, salinity of water bodies are cause spatiotemporal variations in evaporation in various regions as such. Now, this is something that we now move on to in the form of condensation. We have done this earlier. केलंय का नाही आपण हे आधी?
हो सर केले.
कुठं केलेलं आपण हे?
माउंटेन ब्रिज आणि व्हॅली
केले.
ब्रिज मध्ये सर.
And also done as what? Under what category? Inversion of temperature मध्ये केलेलं आहे आपण हे. We are presently looking at it with reference to condensation. Condensation. येतं लक्षात इथे condensation. Okay. Now this is with reference to what is also called as say the different environmental lapse rate. What I'll do is let me check what all I have in for your temperature inversions. Let me see if I can play them for you. हे केलं होतं का रे आपण आधी? मला वाटतं त्या दिवशी केलेलं आहे आपण हे सगळं. आय डोंट थिंक वी नीड टू डू दिस अगेन. व्हॉट डू यू से? हे आपण केलेलं आहे ना आधी. हे तिन्ही पाहिलेले आहेत आपण. हॅलो, पाहिलेले आहेत का नाही पाहिलेले आहेत? ऐकू येतंय ना? हॅलो, कॅन यू हिअर मी?
सर.
हा, मग
Yes,
आता
yes.
शांत कशी काय झालं रे सगळं? हे पहिले दोन पाहिलेत आपण. हे इडियाबॅटिक प्रोसेसेस केलेत का? इडियाबॅटिक प्रोसेसेस आय डोंट रिमेंबर डुईंग देम, बट
हे
लेट मी
सर नाही
कन्फर्म इट
बघितलं आय
फ्रॉम युअर
थिंक.
साइड.
मला नाही आठवत ते
नाही बघितलं
बघितलेलं.
का? ओके, सो विल प्ले दॅट. जरा जास्त आहे पण मी त्याची स्पीड फास्ट करतो. लेट मी सी. Just a moment, let me stop sharing this and I will present. अरे देवा, कुठे गेलं ते टॅब?
which the temperature of an air parcel can be changed. Static processes involve direct energy exchanges. An example is the heating or cooling of the air as it moves across a hot or cold surface. So-called adiabatic processes do not involve net energy exchange. Heating or cooling is achieved by compression or expansion of the air. Here is how adiabatic processes work. Imagine you have air molecules flying around in a chamber. High temperature means that the molecules have high kinetic energy. They're flying very fast. If I compress the air, then the air molecules will start flying faster, which means that the air is getting warmer. When I expand the air again, the air molecules are flying at a slower speed, or in other words, the air cools down. That is an adiabatic process. That begs the question how air in nature is compressed or expanded. Remember that air pressure decreases with altitude. So if an air parcel rises for whatever reason, it will get into a region of lower air pressure. As a result, it will expand and cool. If we force an air parcel to rise, it will expand and cool. If we force an air parcel to sink, it will contract and warm. As long as there is no condensation involved, the temperature of a rising air parcel decreases at a fixed rate. This rate is called the dry adiabatic lapse rate. It is 10 degrees Celsius per 1000 meters. That means if your surface air temperature happens to be 32 degrees Celsius and you force the air to rise up to 1000 meters, the temperature will be 22 degrees Celsius. You force it up to 2000 meters, it will cool down another 10 degrees, so its temperature is 12 degrees, and so on. The opposite happens when you force it to come down. It will increase its temperature again at 10 degrees per 1000 meters. If an air parcel is lifted high enough, it will eventually get so cold that it cannot hold the water vapor any longer. This is the height at which saturation occurs. It is also called the lifting condensation level, because further lifting will cause condensation. Condensation means that water vapor gets from the gaseous into the liquid states. We see the formation of clouds. In this example, the dew point temperature, which as you know depends on the water vapor content of the air, is 2 degrees Celsius. At 3000 meters, the air reaches its dew point, 2 degrees Celsius, so any further lifting will cause further condensation and formation of the cloud. The process of condensation releases energy. Therefore, the rate at which the air temperature decreases from the lifting condensation level upward will be less. The air parcel still expands, it still cools down, but not so much anymore due to the fact that energy is released through condensation. Beyond the lifting condensation level, air parcels cool at the moist adiabatic lapse rate, which is approximately 5 degrees Celsius per 1000 meters. It is also called saturated or wet adiabatic lapse rate. The real value can be between 4 and 9 degrees Celsius per 1000 meters, depending on the amount of water vapor that condenses during the lifting. Remember that the dry and wet adiabatic lapse rates are values for the temperature decrease of a lifted air parcel. These are not values for temperature decrease with altitude that can be measured by taking temperature readings at different altitudes. In Chapter 2, we have already talked about the fact that the temperature within the troposphere decreases with altitude. This decrease of temperature with altitude is expressed by the so-called environmental lapse rate, ELR, which is also named ambient lapse rate. Similar to the other lapse rates, it's expressed in temperature difference per 1000 meter altitude difference. The environmental lapse rate varies with time and place. It depends strongly on surface temperatures. Solar radiation causes surface heating during the day. This generally leads to high temperatures near the surface and consequently a high environmental lapse rate in the lower atmosphere. Terrestrial radiation causes surface cooling during the night, which typically results in a small environmental lapse rate. When the near-surface air is even colder than the upper air, we call this a temperature inversion. The horizontal transport of air, called advection, is another factor that influences the environmental lapse rate. Advection of cold or warm air at different levels, for example due to varying wind direction with altitude, causes changes in the environmental lapse rate. I mentioned earlier that adiabatic cooling occurs when air expands because it is lifted. Four principal mechanisms can initiate the lifting of an air parcel: orographic lifting, frontal lifting, convergence, and convection. Orographic uplift occurs when mountains act as barriers to the flow of air. Air ascends the mountain slope, causes adiabatic cooling. This often generates clouds. Many of the world's rainiest places are located on windward mountain slopes. When air reaches the leeward side of the mountain, much of the moisture has been lost. Air descends, warms adiabatically, and condensation and precipitation are not likely. The results are rain shadow deserts, such as the Great Basin Desert in the western United States and the Patagonia Desert in Argentina. The rising air on the windward side of the mountain range cools first dry adiabatically and later wet adiabatically. The sinking air on the leeward side of the mountain range warms only dry adiabatically. The results are warm downslope winds on the leeward side, such as the Chinook winds in the Rocky Mountains or the Föhn winds in the Alps. A front is a line where cold and warm air masses collide. This causes the lifting of warm air, which is called frontal lifting. A low pressure center, also called a cyclone, always causes air to converge. Horizontal convergence always causes air to rise. Free convection occurs when air is lifted as the result of heating near the surface. This is localized over fairly limited areas and can result in localized thunder showers. The result of the fact. So what makes air rise? In nature, there are two forces working on an air parcel. Gravitational force tries to pull it down to the Earth's surface. Buoyancy force tries to pull it upward. Buoyancy force is simply the result of the fact that we have higher air pressure near the ground, low air pressure in the upper atmosphere, and as a result, air should be moving upward. Given that these two forces, gravitational force and buoyancy force, are at an equilibrium, there is, as of now, no reason for an air parcel to rise or sink. However, that changes when the density of the air parcel changes. If you have an air parcel that has a higher density than its surrounding air, then it will sink towards the Earth's surface. If the density of the air parcel is lower than the surrounding air, then it will rise. But what determines the density of air? The answer is simple. It's the temperature. Lower temperature, higher density. Higher temperature, lower density. So an air parcel that is warmer than its surrounding will rise. An air parcel that is colder than its surrounding will sink.
Sorry,
सर तुम
I
समझ
think we had done this when we were in the class, and the last section we did not do, but I think I remember we have played this for us ourselves. Anyway, it hardly matters if we have seen it again, because these are a bit complex things, and that's why they take some time to actually be understood as such. Now, um, let me just check what I have in store for you all, and accordingly. Uh, Anyways, okay, we'll do one thing. We'll continue with what we have been doing. So I will just represent this here. Mm, Sorry, we are rushing ahead. I will take you back to something else. We will do this thing now. Just give me some time to adjust these things for you all. Okay, now I am ready, and I'll get you to this aspect. Just let me settle down, and I will tell you what we are actually up to. Okay. Um, these are basically various forms of precipitation. Okay. You have dew and mist, which I've already said, and of course, this is fog. So, dew, mist, and fog are more nearer to the surface. Rain is actually falling down. You have hail. Okay. The solid form, and another solid form is snow. Okay. These are the various forms of precipitation. You'll see that normally when you have warm air and cold air. Okay, we have just spoken about this, rather, the commentator has spoken about this in an earlier section, but I'll come to this later once again. Okay, these are the actual photographs of these forms of precipitation or condensation. Okay, here, cloud is a form of condensation. Fog and mist is one. Okay, then you have dew, which is actually condensation as well. Rain is precipitation. Snow and hail are precipitations as such. These are the various types of clouds. Actually, should have been a part of your syllabus. We have not kept it in your syllabus as such. But cirrus clouds are the highest, tallest, and then you have the cumulus, altocumulus, Okay, and clouds are the lowest of these clouds. Nimbo means water. Okay, nimbostratus means water bearing cloud. So maximum amount of rain comes from nimbostratus. Okay, a high amount intensity of rain comes from cumulonimbus. Cumulus, that is growing like a cauliflower. At the same time, nimbus means a lot of water. So you have a thunder and you'll have lightning and you'll have high intensity of rain from such clouds as such. Uh, Now I need to bring you to this. If you remember, we stopped at this earlier, but let me explain to you what you are seeing in front of you. This is actually lapse rate. Sorry, lapse rate. Now, what is lapse rate? We have already seen this earlier. What lapse rate is. Now, on the x-axis, you have temperature split from 0 to 10. And on the y-axis, you have height in kilometers. This is 1 kilometer. Now, contradictory to what you see normally in your economics diagrams or otherwise, this scenario is a bit different in the sense what I'm calling a stable is otherwise. This is a stable thing. Otherwise, you'll see that this has a very steep gradient. But why do I call this as stable? Basically, because even at 1 kilometer, the difference in temperature is just 2 degrees. On the other hand, as far as steep gradient is concerned, which to the eye actually is a smooth slope. Okay, if you go by geomorphology, what is written as steep here is actually smooth, and what is written as gentle here is actually steep. But that depends on these values. Okay, these values. Now, what is happening in the steep slope here is that within half a kilometer, the temperature has fallen from 10 to 0. And that is why this is called as a steep lapse rate. This is called as a gentle lapse rate. These conditions of stability, instability, we are yet to come to that. We are yet to look into other aspects of saturated adiabatic lapse rate and other lapse rate as such. Adiabatic is a process which we have just seen in the clip that we have seen from the YouTube as such. Understand these things, let us move slowly ahead. What happens is you have various types of rainfall. If you remember, they showed this very diagram in the clip also. Okay, orographic rainfall. Orogeny is something that you may have done in geomorphology. Mountain building. Orographic is a rainfall which happens because of mountains. Before we go into the details of that, okay, normal lapse rate is 6.5 is what we have seen. Okay, then there are two technical lapse rates, dry adiabatic lapse rate, which is above 9 degrees. Okay, it could be 9 and it could be 12, 15 also. Okay, you have wet adiabatic lapse rate. The commentator says it is from 4 to 9. Okay, 4 to 9. Normally, let us say it is 4 or let us say 5 or it is 6. Okay, we'll put it max at 6 for our convenience as such. Okay, so normal lapse rate, dry adiabatic lapse rate, wet adiabatic lapse rate. And then they also spoke about what is called as environmental lapse rate. Environmental lapse rate is something, is the lapse rate at a particular place. The environment belonging to the environment of that local area. Okay, let us not go into the details of this. Moving ahead. Convectional rainfall is the second type of rainfall. Okay, this is again a weather condition which we are going to understand. What happens is if a surface is going to be heated faster, the air above it is going to heat. Okay, this will start rising. Because it starts rising, it will start expanding. Okay, because of this, and it is called as adiabatic cooling. Adiabatic cooling. If it goes further up, you'll see that it is going to go further large and so on and so forth. Okay, this is convectional heating. Okay, this is frontal. Okay, you have to imagine this as a box. Okay, this is the complete box you can see here. Okay, this part is the warmer part, warm air, and this part is the cold air. Okay, moving this way and this way. The warmer becoming less dense. Okay, it is just thrust upwards. This is called as frontal wedging. Okay, in the whole scenario now, let us once again revise. What does adiabatic mean? Adiabatic means no gain, no loss of what? Of heat. Then how does the temperature fall or rise? Is because of thermal expansion or dynamic expansion and dynamic contraction. Dynamic is with regards pressure. Now, adiabatic lapse rate normally or environmental lapse rate 6.5 per kilometer. Wet adiabatic 4 or 5 or 6. Okay, this will cause what is referred to as instability. Don't worry, we are going to do all of this. Dry adiabatic lapse rate is 10 degrees and more than 10 degrees, more 10 and more. Okay, this will lead to stability conditions or not. Let us see what is going to happen. When does absolute stability take place? Okay, when your adiabatic lapse rate or your environmental lapse rate is to the extreme left of wet and dry adiabatic lapse rate. Conditional stability is a condition where this will move to the center between them. And absolute instability is when it moves to the extreme right position as such. Okay, that is what we have to understand of this slide. Let us move ahead. This is again something which they have shown in the earlier YouTube clip that we saw. What is happening? The surface temperature, okay, of the air mass, when it rises up by 1 kilometer, it will fall at a rate of dry adiabatic lapse rate, which is 10 degrees. So what starts at 32 by 1 kilometer comes down to 22. Okay, because it has expanded. Okay, the same thing has expanded further. This is the original 22. It has expanded to this size. Because of dynamic expansion, the temperature falls further by 10 degrees. Another 10 degrees, it comes to 12. And this now further going up, this is the original size. By the time it comes to 3 kilometers, it has expanded further. Because it expands further, the temperature falls further. So what started at 32 degrees, within 3 kilometers has come down to 2 degrees. Rising air parcel expands and cools. Exactly opposite, sinking air parcel is going to be compressed and then it's going to be warming as such. This is something that we have to keep in mind. Then, if you are going to bring in condensation level, this is also called as, we have just seen it, saturation. Beyond this point, condensation will take place. Okay, when condensation happens, energy is going to be released. When energy is going to be released, obviously, wet adiabatic lapse rate takes over in this blue portion. Till this, you had dry adiabatic lapse rate. How do you do that? Know that 32 to 22, 22 to 12, 12 to 2. But after that, it is cooling at 5. Okay, this is minus 3. Confusion karun घेऊ नका. This is not 3, this is minus 3. So 2 to minus 3 is 5. Minus 3 to minus 8 is 5. Okay, and if you remember the four mechanisms that cause the rise, again from the clip that we saw earlier, orographic lifting, frontal wedging, he said, convergence, he said, this is more with reference to cyclones, he said. And then this is convection, localized convective lifting as such. Okay, these are weather conditions which will evolve. Okay, I've just explained to you what has been explained here. Okay, when it moves from here to here, the original size expands to this. and from here this original size expands to this. Okay, now what happens is, if at this temperature, about 25, it goes up. Okay, this cools by dry adiabatic lapse rate, and this has an environmental lapse rate which is 5 degrees. This will be condition. Okay, एखाद्या एरियामध्ये हा चेंज असू शकतो कुठलाही. Environmental, locally it will change, but this is a mathematical number. Okay, so 1 kilometer, this goes down from 25 to 15. However, this goes from 25 to 20 only because of this 5. Okay, another 1 kilometer, this comes down from 15 to 5, but this has come down from 20 to 15 only. Now what happens? The temperature along this line is actually 15 degrees Celsius, sorry. And that of this air particle is 5 degrees centigrade. Okay, that makes this denser. Because this is cold, this is denser. And that is why the tendency of it is going to be coming down. It will try and come down. Okay, this is stable atmosphere. Okay, an unsaturated parcel. Okay, and then we are going to have a few conditions which we will take up tomorrow. There are 3 conditions that we need to understand. What are these 3 conditions? Absolute stability. Then we are going to have absolute instability. And then you are going to have conditional instability. This is nothing but frontal wedging, DGE, and this is nothing but convectional ring. Okay, so we have to understand this. Because it is going to take time, we will not do it today, we will do it tomorrow. I will stop here for the moment. I will stop this in the show, discard. Yeah, and just in case you have any queries for me, you can please ask me your queries. Anybody having any queries?
सर ते स्क्रीनशॉटचे असाइनमेंटचं सांगणार होते तुम्ही आज.
Screenshot assignments. Yeah. I had asked you all to take 2 places, बरोबर?
Yes, sir.
And
Yes, sir.
take screenshots for various parameters of the weather, बरोबर? And then you were supposed to make what? An interpretation of that individually, बरोबर?
हो सर.
And that is how you were supposed to be making a digital assignment for that.
Okay, sir.
हा, तर ही असाइनमेंट तयार करायची आहे तुम्हाला. आणि आता ह्याला बरेच दिवस झाले, पण तरी सुद्धा मी तुम्हाला थोडासा वेळ देईन. यू विल हॅव टू सबमिट इट बाय संडे. त्याची असाइनमेंट मी क्रिएट करतो आणि यू कॅन सबमिट इट इन द क्लासरूम अकॉर्डिंगली. सगळे क्लासरूमला जॉईन झालेले आहेत का रे?
हो सर, झालंय.
एव्हरीबडी हॅज जॉईन्ड. आय विल चेक ॲट माय
Yes,
एंड.
sir.
या 17 लोकांपैकी कोणी नसेल तर आय विल जस्ट रिमाइंड, इफ यू हॅव नॉट जॉईन द क्लासरूम, प्लीज सी दॅट यू जॉईन द क्लासरूम ॲज वेल. आरती पूल नाही वाटतं आज, मला दिसत नाहीये ती. ओके, सो सी दॅट यू डू दॅट. आणि द लास्ट रिटन असाइनमेंट दॅट आय हॅव टोल्ड यू, त्याचे टॉपिक काय होते रे? दॅट ऑल्सो आय वॉन्टेड टू डिस्कस विथ यू. शेवटची
Circulation of
रिटन
atmosphere.
Pressure belt.
pressure belt, circulation of atmosphere, pressure
Circulation
belt,
of atmosphere
wind
and
system.
developing wind
Yes, sir.
system.
Gradient wind.
Geostrophic wind.
Geostrophic wind.
हा, तर ही असाइनमेंट जी आहे ही तुम्ही संडे पर्यंत सबमिट करायची.
Okay,
मला
sir.
फक्त लिहून घेऊ दे.
Okay, sir.
Sir.
एक मिनिट.
Okay, sir.
सर्क्युलेशन ऑफ,
सबमिट करायची का?
एक मिनिट. सर्क्युलेशन झालं, प्रेशर बेल्ट झालं, विंड झालं, ग्रेडियंट विंड झालं, बरोबर? आणि जिओस्ट्रॉफिक विंड.
Geostrophic wind.
जिओस्ट्रॉफिक विंड सांगितलं मी तुम्हाला. एवढीच आहे ना?
हो
हो सर, एवढंच आहे.
हो
ओके.
सर.
मंडेला करतो म्हणताय का तुम्ही?
नाही सर मंडेला कॉलेज आहे ना ऍक्च्युली. आज न्यूजला ऐकलं की मंडे पासून चालू होणार आहे सगळे कॉलेजेस आणि स्कूल.
बघू आपण, बघूयात. थांबा जरा,
ठीक
काही करू नका.
ठीक आहे. ठीक आहे
कारण
सर.
कसं होतं, परत वर्गात कमी मुलं येतात, काही लोक गावाकडे असतात. ओके, लेट द प्रिन्सिपल फर्स्ट कम आउट विथ अ नोटीस अँड लेट अस सी what and then let us see what is going to happen accordingly.
ओके सर.
So assignment, key assignment, latest assignment, and the assignment on
वेबिनार.
नाही रे, मी आता
स्क्रीनशॉट
कसली म्हणत होतो,
स्क्रीनशॉट
स्क्रीनशॉटची
स्क्रीनशॉटची
असाइनमेंट,
सर.
वेदर अँड
Weather
रडार,
and
हे
radar.
दोन्ही संडे पर्यंत होऊ शकतील. संडे पर्यंत होऊ शकतील ह्याच्या सबमिशन्स.
सर पण काय करायचं परत एकदा सांगा ना, वेदर आणि रडार.
हा सर, वेदर अँड रडारचं म्हणजे
अरे तुम्ही
आम्हाला
एक
फक्त
प्लेस घेतलेला आहे.
इंटरप्रिटेशन लिहायचंय का?
तुम्ही
हो,
जे म्हणला ना
तुमच्याकडे
त्याच्यावर
येस, तुमचे जे स्क्रीनशॉट्स आहेत त्या स्क्रीनशॉट्स वर तुम्हाला इंटरप्रिटेशन करायचं आहे. तुम्ही किती दिवस सांगितले? मी तुम्हाला 10 दिवस सांगितले तुम्हाला, बरोबर?
नाही सर, 25 तारखेपासून 1 तारखेपर्यंत.
आठवड्याभर सांगितलं होतं.
पाच
हो
आठवड्याभर
पाच
सांगितलं.
सर त्याची म्हणजे असाइनमेंट करायची का?
25, 26, 27, 28, 29, 30, 31, 1, 8 दिवस झाले ताई. 5 दिवस नाही
हो
होत.
सर.
हा, या 8 दिवसाचे सगळे तुमच्याकडे जे काही असतील आता, की जे काही असतील, कोणी वेगळे घेतले असतील, कोणी वेगळे घेतले असतील, जे काही तुमच्याकडे स्क्रीनशॉट्स असतील, याचं इंटरप्रिटेशन ऍट व्हेरियस लेवल्स करायचंय तुम्ही. त्याची एक डिजिटल असाइनमेंट बनवायची, तिची PDF करायची आणि क्लासरूमवर सबमिट करायची. हे सबमिट करायच्या आधी मला सांगा, मला आधी तुम्हाला ती असाइनमेंटसाठी स्पेस क्रिएट करावी लागेल. मग तुम्हाला ती असाइनमेंट सबमिट करता येईल. ती बहुतेक आज, आता मला जसा वेळ मिळेल तशी मी करतो. आणि वेबिनारचं आपल्याला सर्टिफिकेट, मी आज त्यांच्या मागे लागलेलो आहे. आज बहुतेक आपल्याला सर्टिफिकेट्स येतील आपली. त्याची सुद्धा काय असाइनमेंट करायची थोडीशी आयडिया मी तुम्हाला आधी दिलेली आहे. ओके, बट आय अगेन रिपीट the requirement as far as the webinar assignment is concerned. We don't have the time to go into a discussion वगैरे वगैरे. So I will cut short that assignment. Let us see, but I will announce that assignment tomorrow. As for now, ह्या 2 assignments see that you complete by Sunday and upload it on the Google Classroom, which to which you have joined. ओके, याच्यामध्ये काही कन्फ्युजन आहे?
नाही सर.
नाही सर.
ग्रेट, थँक्यू. आपण आज थांबूया तिथे. उद्या आपल्याला हे थोडंसं अजून परत डिटेलमध्ये करायचं आहे. आज जे आपण सगळं केलेलं आहे, आय होप यू हॅव अंडरस्टूड. इफ यू हॅव नॉट मेक डाऊन पॉइंट्स, काय समजलेलं नाहीये, टुमॉरो यू कॅन आस्क मी अबाउट इट अँड वी विल आय विल ट्राय टू री एक्सप्लेन व्हॉट यू मे नॉट हॅव अंडरस्टूड.
सर, कालचं लेक्चर तुम्ही युट्यूबला पोस्ट नाही का केलं?
अरे हो, कालचं पण राहिलंय, आजचं दोन्ही करतो मी. थोडासा बिझी होतो मी मीटिंग्स मध्ये. करतो.
ओके सर.
तर तुम्ही वेदर आणि रडारसाठी केली असाइनमेंट ह्याच्यावर क्लासरूमवर?
कुठं सबमिट केली? मी असाइनमेंट क्रिएटच नाही केली.
नाही
वेगळ्याच
नाही
असाइनमेंट मध्ये टाकून
तर
दिली.
केलीये तुम्ही असाइनमेंट क्रिएट म्हणजे
केली
सर
assignment
तुम्ही.
लिहिलेलं आहे.
अरे त्या रिटर्न
हो सर.
असाइनमेंटची जागा केलेल्या आहेत मी तुम्हाला. लेट मी
हा सर.
चेक, मी सांगतो तुम्हाला. ओके, नो इश्यूज. ओके, दॅट्स ऑल. बाकी काही नसेल तर लेट मी स्टॉप द रेकॉर्डिंग. अँड